So hi everyone, my name is Emily and I'll be leading today's workshop on introduction to the Python libraries NumPy and Pandas. And I guess just a little bit of introduction about myself. I'm from the University of Waterloo and I study statistics and computational mathematics. And right now I am in fourth year. So I am in the co-op program as well. So I have been taking some co-ops in the data science field. So Python, especially these two packages that I'll be talking about today, are very useful for that case. And I will start sharing my screen. And let's begin. Okay, so an overview, there's brief talk about setup, but I already did kind of, and then I'll just do a really high level introduction on NumPy, what it is, and then the functions in there and how to use it. And also we'll jump into Pandas, again, what it is, the functions in it and how to use it, and then just a brief comparison on those two libraries, and then a list of resources that I use to prepare this workshop. And if we have time, we can have a Q&A session. So for setup, as I said earlier, I'll be using Jupyter Notebook to walk through code and do my demo. And that one, I downloaded Anaconda, and through the Anaconda Navigator, you can open Jupyter Notebook very easily. Or you can choose to use Python plus an IDE of your choice. And there are many other platforms where you can write Python code and run Python code, like people said in the chat. So there's like Visual Studio Code or Google Colab. So feel free to use whatever is accessible to you. Okay, let's get right into this. So what is NumPy? It is an open source Python library for working with numerical data, and it contains a data structure called array. It can be in like one-dimensional up to like two-dimensional up to multi-dimensional, and then it contains very fast and efficient methods that operate on these array structures. So you can manipulate them, you can do math on them. And one thing to note is that the elements of the NumPy array should be homogeneous, which means if you have an array of integers, every element in the array should be integers. So you can't really mix different data types into one array. And one thing that NumPy arrays are better at than as compared to Python lists is that it is more compact. So it is very memory efficient. And to import this library, we just say import NumPy as NP. NP is the abbreviation, is the conventional abbreviation for NumPy. So just usually put that first in your code. Okay, so how do we create NumPy arrays? A very easy way is to initialize them from Python lists. So as you can see here, the syntax is np, which is the library, dot array, and then we have round brackets, and in the round brackets we just put in a regular Python list to initialize the array. So right here I have a equals np.array and 1, 2, 3, 4, 5. So that is a one-dimensional array. Then B is actually a two-dimensional array. So in order to create a higher dimension array, we have to nest the square brackets. And so we have a Python list of lists, and it will create an array. You can think of it as a matrix. It'll be 3 by 2. So in the first row, it'll have 1, 2, and then second row will have 3, 4, and then third row will have 5, 6. And then there are some other built-in methods to create basic arrays. So for example, there is the zeros method, and this one just gives you, once you specify the length in the brackets, so here I have zeros 3, it'll just give you an array of 3 zeros. And ones works in the same way. Ones 3 gives you an array of 3 ones. And then an interesting one is the empty. So again, you specify the length in the brackets. This will give you an empty, okay, the name is empty, but it's actually not an empty array. It'll give you an array of length 3, where each element is just random. Wherever the system can find memory, like the data in that memory could be totally random, and you'll just get an array of length 3, and then you can initialize each element later on. You can work with that. And other techniques for initializing arrays, there is a range. So here, the first parameter is the beginning of your range. The second parameter is the end of your range. And then the third parameter is to specify how, like the gaps in the range, to jump by how much. So here I have 1, 7, 2. That means I am creating an array of 1 to 7, not inclusive of 7, and jumping by 2s. So I get an array of 1, 3, 5. And the last one here is linspace. And this one creates an array of equally spaced elements of what you specify. So here I have 0 to 10. And the number of elements I want in the array is 5. So it will give me 5 elements between 0 to 10 spaced evenly. Oh yeah, if I'm going too fast, please let me know in the chat. I will check the chat. And if you have any questions, feel free to type in the chat as well. And hopefully I will check the chat regularly. Okay, so I'm just gonna go to my Jupyter notebook and kind of show you what I just talked about. So as I said, to work with NumPy arrays, you will want to import NumPy first. Yes, so someone in the chat asked, if we don't remember these functions, is there a place to find good documentation on those functions? Yes, for sure. I myself, I don't even remember everything. I write code in different languages, and sometimes I don't remember the syntax. Sometimes I mix up the different functions. So I will talk about that in the resources section later on, but just quickly, if you want to look at it right now or have it handy, you can just Google NumPy, and there is this numpy.org documentation, and there is a beginner's guide and also a very comprehensive user guide. So if you want to open that up somewhere along, definitely feel free to do so. Okay, going back to my code. Okay, yes, I will import NumPy array as, I'll import NumPy as NP. And then these were just the examples I had on my PowerPoint creating these arrays. So I can actually run this code and show you what it looks like, what the object looks like. So for instance, A, the system will just recognize it as this array object. And then for B, it's a 2-dimensional. It will format it nicely for you, and you can see it, you can think of it as a matrix, and that is a 2-dimensional array. And of course, NumPy supports multi-dimensional, so you can actually do more nested square brackets and bring it up to like 3 dimensions. But I will keep my examples simple for now. Okay, and all right, going back here. All right, so now let's talk about a little bit about data types. So as I said before, NumPy arrays only allows homogeneous type arrays. So in one array, it has to be the same data type. And some of the common ones that are supported are integer, float. So floating point are like numbers with decimals. And then Boolean, which is true or false, string, and then complex. I'm not going to talk a lot about complex or string or Boolean because what NumPy does well is working with numerical data. So I will focus on the integers and floats. So here, when you initialize or create an array, you can actually specify what type of data you want, especially between integer and float, because sometimes when you initialize it, it will probably recognize it as an integer instead of float, but you want it to be a float. So here, an example is using a range 3, which means I want an array range 0 that is 0, 1, 2. So remember, Python is 0 base. Every time you specify a range or indices, it starts at 0 and it doesn't include the last one. So it counts from 0. So this one, I specify the data type I want by using this parameter called dtype. And then I give it the value np.int8. So for integers and floats, you can specify how much memory you want to allocate. So 8 would be like 8 bytes, and then there's 32, and then there's 64. So here, yeah, I just wanted integer with 8 bytes. And that gives me an array of 0, 1, 2. And another example is I want to specify, I want my elements to be floating point values. But I just initialize it writing like 1, 2, 3 as integers. Like Python will just recognize it as integers by default. But I want them to be floating point values. So I specify it, and you can see that it will represent it as floats by putting in a decimal at the end of these numbers. And it gives me an array of 1, 2, 3. Okay, and the dtype syntax, you can actually check the data type of your array. So here I have h.dtype, which returns int 8, which is what I specified earlier as the data type of the elements in my array H. And one last thing in this part is that you can convert data type of array elements. So the example here is I initialize my array I as floating points, but I wanted to convert it back to integer. So I would just do this syntax, np dot the data type you want to convert to, and then the array that you want converted. And then if I, the output, it will give me that this array is int 8. Okay, I will go back to here. And yeah, this is just the examples I talked about. So we can look at the data type of the array, and we can also convert the array. And then we have some array properties that we can check. So first of all, I'll use this array example here with the 1, 2, 3, 4, 5, 6 matrix. And we can check the rank of the array, which is the dimension, the number of dimensions. Here, the syntax is your array dot ndim. And if I run that, it gives me 2 because this array is 2-dimensional. We can also check the size of the array. And a very simple syntax, the array dot size. And that gives me 6 because there are 6 elements in total. And we can check the shape of the array with array.shape. And that gives me the 3x2, which is how you think of this 2-dimensional array, like 3x2 matrix. And then we can also reshape arrays. So with this syntax, array.reshape, I can change the 3x2 array into a 2x3. And the output will be the array where it becomes 1, 2, 3 in the first row, and then 4, 5, 6 in the second row. Okay, I will actually go here and just show you live. So we have the dimensions of the someone in chat just asked, is this HTML? No, this is Python. And we are talking about 2 Python libraries, NumPy and Pandas. And right now we're talking about NumPy. Okay, so as I said, yeah, this one I'm using the array that I defined earlier, B, which is the 1, 2, 3, 4, 5, 6. So number of dimensions is 2. The size is 6, and the shape is a 3x2 2-dimensional array. And then reshaping the array, it will show you it becomes this, a 2x3 instead of a 3x2. Okay, and now we can talk about accessing arrays. So the example I'm using here, array X, it's a range 10, which means it's an array of 0, 1, 2, 3, 4, 5, all the way up to 9. And we can index arrays using the square bracket syntax. So for example, X of 0, just another reminder, Python counts from 0. So X of 0 will give us 0, which is the first element in the array. And you can also put in negative indices. It will just count from the end. So X of -2 will come from the end. So the last element in the array is 9, and then that's -1, and then 8 would be -2. So it's probably better if you can like visualize the array as this strip, and then yeah, just count from one end or the other. There's also you can also index two-dimensional arrays, and it's pretty similar. So right here, I just reshaped X into a 2x5 instead of a 1x10 array. This is like another way to reshape the array. And if you actually only include one index, so X of 0 on a two-dimensional array, it will give you the first row pretty much. So it will give you the first row as an array. So if you don't want that, if you actually want to access a single element in a multi-dimensional array, you can do this example I have here, X 1, 2, which would mean I want to access the second row, third element of the array. And then the equivalent syntax is to use the square brackets 2 times, but I personally like the comma syntax because it just saves me from typing so many brackets. And then slicing arrays, again, on the original 1x10 X array, we can use this syntax with colons. And the first indice means the starting index. The second indice is the ending index. And then the third one is how much to jump by. And in this example, if you include all 3 indices, it's very specific. And I want from the second element up to the last element, and then jump by 3s. So I get an array of 1, 4, 7. And then if I only specify 2 of these indices, I would just get all elements between the range. So here I get all the elements between position 2 and position 5, but not inclusive of position 5. And lastly, if you can also only specify 1 index with the colon, then it will, so here I have 7 colon, which means I will get the array starting from index 7 all the way till the end of the array. Or if I do colon first and then 7, then I will get the start of the array all the way up to index 7, but not including index 7. Okay, let's go and actually see this live. So here I have X, and I guess to better visualize it, this is my array, 0 to 9. And x of 0 gives me the first element. X of -2 gives me the second last element. And here I'm just reshaping X to show you two-dimensional indexing. X of 0 gives me the first row. You can still think of it as the first element if you look at the array like this. So it's a list of lists, right? So the first element of the outer list is a list, is the first list here. And then if you want to access a single element, you can use this syntax or the equivalent syntax here. And you see both of them give us 7, which is the second element, second row, third element. Okay. And then on slicing, so I just redefine my X to be the one-dimensional. And here we can see slicing from 1 to 9. Wait, 1 to 9. Oh, actually, I don't. Yeah, 1 to 9, which is the 10th element, but not inclusive, and then jump by every third element. So we have 1 and then 2, 3, 4, 2, 3, 7. And similarly, here we have the other two slicing examples. Here's just 2 to 5, but not inclusive. And then the 7 colon is just 7 until the end. And this slicing actually works on two-dimensional arrays as well. You can, I don't have an example here, but you can read more about that in the NumPy documentation. Okay, let's move on to array manipulation. So actually, maybe I'll just talk about everything on here. Okay. Instead of switching back and forth. So here I have 2 arrays. One of them is just array 1, 2, and then one of them is 3, 4. And notice that they are of the same dimension and size. And one thing you can do with arrays is actually stack them or combine them. Here, I will do a horizontal stack, so H stack. This is the syntax. We have, we pass it the arrays we want to stack together in round brackets, and then it will stack it for us horizontally. So this is kind of like a concatenation, and it gives back a one-dimensional array. We can also vertically stack these 2 arrays, and the syntax is vstack for vertical. And the result, as you probably could have guessed, it would just stack it vertically like building blocks, and we get a 2x2 array. So another thing we can do is combine different methods that we have just talked about. So here I wanted a big array, and I didn't want to type out everything. So I just used a range 1 to 13, which gives me an array actually just 1 to 12. And then I combine this A range, which is an initialization of an array, with the reshape method, and I make it into a 3x4. So I specify 12 elements, and I want it to be a 3x4 array. So here is the output of that code. So yeah, if you don't have this reshape, then the A range would just give you a 1x12, one-dimensional array. But then combining that in one line of code, I can get a 3x4. And then in reverse of a stacking operation, we can split arrays. So here is the syntax. It is hsplit, and you pass it the array you want to split up. And the second argument is how many arrays you want it to split into. So here I just set 2. So it will split horizontally and give me back the 2 arrays. It just splits horizontally, so like here down the middle. And it gives me the one to the left and then the one to the right. You can also be more specific with this. And in the second parameter, instead of passing only just one number and the system will just split it evenly, you can pass it a tuple, and this will specify after which column to split at. So here I split at after column 1 and then after column 3. So this is the output, and you see that you get back 3 arrays. Splitting at after column 1, I get an array of just the 1, 5, 9. So this is different than like a one-dimensional array. This is actually a 3x1 array. And then I get the middle 2 columns as the second array. And the last one is just what's left after column 3. Okay, any questions so far? See in the chat. But again, if you have questions, feel free to ask. I hope I'm not going too fast. And don't be worried about like remembering or memorizing all these functions and syntax I talk about. Okay, someone in the chat wants me to explain the tuple part again. So here, instead of passing in just one number, we can pass in a tuple, which is like in these round brackets, and each I guess number in here will specify where to split in your array, like after which column to split. And because I'm using hsplit, so it's a horizontal split. So here I have 1, which means this is the first. If you think of this as the first column, it will split here after the first column. And then 3, it will split here after the third column. And that's why it gives you back this array. So the split is here. It'll give you back the 1, 5, 9. And then the second split is here. It will give you what's in between the 2 splits. And then after the second split, there's no more splits. So it just gives you whatever's left, which is the 4, 8, 12. Yes, okay. Hope that answers your question. Okay, if no more questions, I'll keep going. Let's see. Oh, yes. All right. We can talk about copying arrays. So one way to, this is actually like another way you can create an array, which is after you slice an array, you just like equate it to a new variable, and this variable will have that. So here, I have A, which is probably show you what A looks like. Oh yeah, A is just up here, the 2-dimensional array. And I did say earlier that you can also slice on 2-dimensional arrays. So here you just use a comma to separate it. The first parameter or index will specify which row, I guess, you want, which rows you want, and then the second, after the comma, will specify which columns. So here I have 1, which is the second row. And then I have just a colon with nothing else, which means I want everything, every column of the second row. So that's another syntax that some of you might already be familiar with. So yeah, I want this second row and every column of it, which gives me 5, 6, 7, 8. And I put it in the variable B. So now this type of copying arrays, so like if I actually say like B equals A, this type of copying arrays is actually only a shallow copy. It's what we call a shallow copy. And if I mutate B, so I'm going to say B, the third element in B, I want it to be 9 instead of 7. So I'm mutating B now. So B becomes 5, 6, 9, 8. What happens to A? So this is only a shallow copy, which means that A also gets mutated. And we see that A, the second row of A, actually becomes 5, 6, 9, 8 as well. So this is usually something we don't want. Someone in the chat asked, so B is just a reference to A. Yeah, you can think of it that way. You can think of B as just like pointing to A, and A is still the actual object that exists, and B just points to it. So yeah, this is a shallow copy. It might not be something we want. Usually it's something we don't want, because we don't want to accidentally mutate arrays. So to do a deep copy, actually copying A over and like actually creating a new object C here, instead of just having your variable point to the old object, we can actually use this method, which is called copy, very straightforward, and we do the array A dot copy, and then that will give us a deep copy. So C, I know here A is already mutated, but we will say C is this mutated A, and then we try to mutate C. So here, we have C, third row, and third row, first element. We change it to 7. We change the 9 to 7. Okay, so C is this array now. So we have here 7, 10, 11, 12. And as you probably could guess, A stays the same. A does not change because this is a deep copy. So A here is still 9, 10, 11, 12. Any questions about shallow and deep copy? And of course, there are like pros and cons to both. If you are sure you're not going to mutate your new array, then you could do just a shallow copy. It will probably be more efficient and work faster, especially if your array gets really, really big. But if you want to make sure you're not accidentally mutating the original array, you will have to do a deep copy using this copy method. All right, now let's talk about array operations. So you can actually do arithmetic on arrays, just like you would do with like matrices. So here I have, again, these two very simple arrays defined A and B. And the syntax is very simple. A plus B, you can do, addition, subtraction, multiplication, division, and these will do element-wise operations. What do I mean by that? Let's just see. So here, A plus B, it will take, oh yeah, you should do these operations on same-sized arrays. It doesn't really work well. It doesn't really work if you try to do it on arrays that don't match in size or dimension. So here, A plus B becomes 4, 6. It just element-wise adds up the two arrays. So here it's 1 plus 3, and then the 2 plus 4. And it gives us back an array of the same size. And then similarly, subtracting, here I did B minus A because I didn't want to end up with negative numbers, so I used the larger one, subtracting the smaller one. So it's just 3 minus 1 is 2, and 4 minus 2 is coincidentally 2 as well. You can multiply arrays, and this doesn't do like matrix multiplication or anything. It just does element-wise multiplication. So 3 times 1, and then 4 times 2. So it gives us 3 and 8. And lastly, division. And notice that it gives us back floating points. So this is what will happen when you do division. Even if you have like arrays with integers, it will become floating point values. And here is just 3 divided by 1 and 4 divided by 2. Other operations you can do is like scalar multiplication on an array. So here I have C as this array, and I'm gonna say that this is, for example, a temperature array. It indicates temperature in Celsius, and maybe you want to convert it to Fahrenheit because you're in the United States. And you can do this. So C is an array, but you can actually just multiply like scalar values and add and do arithmetic on that array, and then you get the result. This is called broadcasting. It will broadcast each scalar to every element in the array and perform the operation specified. Yeah, this is about broadcasting. Okay. Okay, there are some more operations you can perform on arrays that are very helpful to like analysis, or if you're doing some statistical analysis, these are good summaries to have. So I call these aggregate functions because of their nature. So here I have x, which is 1 to 10, and one-dimensional array 1 to 10. And I do x dot sum. So this is one of the functions. You can sum up everything, all the elements in the array, and it gives us 55. You can find the minimum element in the array, and that's 1. You can find the maximum, it's 10, and you can also find the mean. So these are very simple. You can also find the product of the array. So here I have 1 to 10, right? So if you have the product, it'll be 10 factorial. And if any one of you recognizes this, it's 10 factorial. And you can find the standard deviation of your array. There is 2.87. Now, these things, all these functions, you can do similarly on arrays of more than one dimension. So here I define another array called y. This is a 3 by 3. And with two-dimensional arrays, you can actually specify something. You can specify the axes in which to perform this aggregate function on. So here I have y dot sum axes equals 0. And this means that I am summing up over the columns. So here, summing up over every column instead of summing everything. So I get back an array where the first element is the sum of the first column, and then the second element is the sum of the second column, and so on. And of course, you can do an axis equals 1, which will be row-wise operation. So here, just to use a different function, I used mean, and I specified axis equals 1, which will give us the means across the rows. So, and this is like pretty simple example because these numbers are consecutive, and then the mean is just the middle number. But here it gives us the 2, which is the mean of the first row, and then 5, the mean of the second row, and so on. And also it gives it back in floating points because, as you know, when calculating mean, there is a division involved. So it will give it back in floating point value. Okay. And there are some other array methods that I will just quickly go over because I know these are pretty useful. You might not need to use them. So here we have np.unique. And this one, if you have an array with duplicate values in there, like this one that I created, it will just remove all of them and return back all just the unique values, all the distinct values. So when I run that on this array, it will just give me back an array without any repeating values. You can also add this parameter called return index equals true, which will return back an array of indices of the first occurrence of a unique value. So here 0 is the value corresponds to the value 1. And then it's like, oh yeah, 1 has been counted before, 1 is another duplicate. And then here 3 is the index of the next unique number in the array. And then so on. So that might be useful if you want to know the indices or like the positions of the unique values. And then you can also have this parameter, which is return counts equals true. And that gives you the counts of the duplicate values. So here, 1 repeats, 1 occurs 3 times, so this is 3. Then 2 occurs 2 times, it's 2. And then 3 occurs 1 time, it's a 1. So this might also be helpful depending on what you want to do. And of course, you can do this with 2-dimensional arrays. So here, if you just run unique on this 2-dimensional array, if you don't specify an axis, then it will flatten the array for you. And you just get back all unique values, but in a 1-dimensional flattened array. If you specify an axis, then it will search for unique elements depending on the axis. So here, I said axis equals 0. It's for unique rows. So this one, there was a row that repeated, which is 1, 2. And you see here 1, 2, 1, 2. So it removed one of the rows. And when its axis equals 1, it will be for unique columns. Okay, next will be the transpose function. As I said earlier, you can think of these arrays, like especially 2-dimensional arrays, as matrices. And sometimes it is useful to transpose them. And you can just use this built-in function here called transpose, or it's simply just .t. And you can see that it just flips the rows and columns. So the rows become the columns, and then the column becomes the rows. Speaking of flipping, there's actually a flip function, and this reverses the order of the elements in the array. So here, going back to this duplicate array, before I started from 1, and now I just like flips it and it's like 10, it's reversed. You can also do flip on a 2-dimensional array. This one, it flips the rows and the columns. So before, show you. So before it's 1, 2, 3, 4, 1, 2, 5, 6. So if first, actually, I don't know the order that it flips, but let's just say it flips the rows first. So the 1, 2 goes to the very bottom, and then the 3, 4, another 1, 2, and then 5, 6 becomes the very top. And then it also flips this way. So that's why the resulting array will be like this. However, if you specify an axis, then it will only flip around one of the axes. So axis equals 0 will flip only the rows, and axis equals 1 will flip only the columns. And here as an example, I said axis equals 1, and you can see that like the 1, 2 thing is still at the very top, but it's just flipped. The columns are flipped. And you can also only just reverse one row or one column. And here, just as an example, you just pass in the column or row you want to flip, and it will only just flip on that one row or column. And there's a flatten function as well. And here we run into the issue of like shallow copy or deep copy again. I won't go too much into it. Just know that flatten will flatten your two-dimensional array into one-dimensional. But flatten will only be a shallow copy. So if you like, for instance, actually assign it to a variable and then you mutate on that variable, the original D2 array will also be mutated. So if you want to avoid that, you can use this function called ravel, and it pretty much works the same way as flatten, but it creates a deep copy. So as you can see, the output is the same. It's the only difference is that one is a shallow copy and one is a deep copy. And lastly, for NumPy, we have generating random arrays. I won't go too much into this because there's like a whole lot on random number generation and using random generating functions. But here is just a simple way to get yourself an array of length 3 of random floating point values. This one, I guess I'll explain this. This one is just the built-in function, and here you can provide it a seed, and then it will perform random number generation based on your seed. So I give it a 5, and you can see it's like these 0.8s and then 0.5. But if I change it, for example, to 0, it'll give me a different set of values. And the syntax here to generate this array is just using the random number generator dot random and then the length of your array. And just another way to do this, if you want an array of random integers within a range. So here I said integers within a range of 0 to 4, because I said 5, so it's a range of 0 to 4. And then the size of my array, I specified I want it to be 2 by 4. Then it will just randomly give me integers between 0 and 4 inclusive in a 2 by 4 array. And we see that the data type here is integer because I used the integers method. Okay, someone asked in the chat what I mean by seed. So seed is like a thing you use to, so this, we're talking about random number generation. And if you want to have reproducible results, for example, you're writing code and you want to see if you're testing code and you're running it multiple times. If you don't give it a seed, it's going to, the random generating part is going to give you different results every time, and you can't really track your code and see if it's working properly. So giving it a seed, it just tells the system that like I'm kind of following this, like I have the seed, so if I run it multiple times, it will give me the same randomly generated numbers. So if I change back to seed is 5, you can see that it still gives me the 0.8, 0.8, 0.5 numbers, right? So if I run this again, it's still going to give me these 3 numbers. And if I need to have reproducibility in my code to check if it's working well, this is like useful. So does that answer your question? We just call it a seed. It's just like a number we pass in so that the system can know what to generate. All right. Okay. Okay, I think that's all for NumPy. These are just, I just went through various methods and how to work with NumPy arrays. If you have any questions, make sure to put it in the chat. Just looking at the time right now, I'll go to Pandas. But yeah, if you have questions, you can just drop them in the chat. So Pandas, what it is similar to NumPy. It's an open source library in Python, and it's a very good data analysis and manipulation tool. So it's very suitable for working with tabular or matrix data with potentially heterogeneous columns. So here you don't need your whole data frame to be of the same data type, as long as usually your one column is of the same data type, but even then it doesn't need to be. And it could be used for ordered or unordered time series data, and it also provides very fast and flexible data structures that I will talk about shortly. And it's a good tool for data tasks in all stages of data analysis. So for instance, starting from the beginning, you have to clean the data and then manipulate it, transform it, and then perform analysis. And even at the end, you have to do some data visualization. So Pandas is a really good package for all of these tasks. And as before, to use it, you just import Pandas as PD, and PD is the conventional abbreviation for Pandas. Okay, so I promised I'll talk about Pandas data structures. So one-dimensional one is called series, and it is a labeled homogeneously typed array. So you can think of this as similar to a one-dimensional NumPy array, but here we call it series. But the more useful and important one is the two-dimensional one called data frame. And this is a tabular structure with potentially heterogeneously typed columns. And each column in the data frame is a series. So that's how they're related. You can think of the data frame as a container for a series, for multiple series. And then it can store different types of data. So some of the types include characters, integers, floating point values, or even categorical data, and many more. Okay, and working with data frames, let's talk about input-output. Usually, because data frames are quite large, we don't initialize it or create it like we did with the NumPy arrays, where we just like actually type out the elements and stuff. We usually read from a file that already contains the data. Here I will focus on CSV and Excel files because that is pretty common. And the syntax to read from a file is just pd.read and then like the file type. So here I have pd.read_csv, and then in brackets you provided the file, the path to the file, and the path is like, if you have your CSV file in the same folder as your Python code, then you can just give it the file name. But if it's somewhere else, then you would have to provide the path to it. And similarly for reading Excel as well, but just in addition, you can provide it a sheet name so that it knows which sheet to read in case you have multiple sheets. And writing, once you like read it in, you might have done some manipulation with your data. Oh yeah, by the way, once you read it in, this CSV data underscore data variable or Excel underscore data variable, these become Pandas data frame structures just automatically once when you use this function to read in these files. These are data frame structures, and after you do your analysis with these data frame structures, you might want to output them back into a file, and then that is done with the to_file type functions, and just provide it the file name you want it to be, and then the sheet name for Excel file. Here there is an index, and by default it's index equals true, which will include in your output file the row indices. So like it will just number your rows 1 to however many rows you have. But sometimes or oftentimes you don't really need that, or you might not want it. So I usually just put index equals false. And then other file types that you can read or write to include the JavaScript object notation, and then like HTML, XML, SQL. So all these I will not touch upon here, but just know that Python Pandas is very flexible, and you can, I guess, connect it to many different file types. Okay, so I will go into working how to work with these data frames, just the basics. I will talk about all these things. So I will go back to Jupyter Notebook. All right. Here I will actually, first import pandas as PD, and then I will actually use a very famous data set called the iris data set. So I have it as a CSV file downloaded, and I have it in the same folder as my Jupyter Notebook. So that's why I just said iris data equals pd.read_csv, and then the name of the CSV file. I don't know if you have this data set, but it's very easy to find on like Kaggle or other places. And it's a very simple data set. So let's just look at this data set. So if you don't have it, sorry, I might not be able to like code along with me, but I will make sure, I will walk you through all the code and make sure you understand what this data set is. So once you read from a CSV file and put it into a variable, this variable, as I said earlier, is a Pandas data frame. If I just want to look at it, I just type the variable, and then it gives me the data frame in a very very nice format in like a table. And Python will automatically like give you these indices for the data frame. And then from these are the column headers. And from ID all the way to species, these are actually like data of a part of the CSV file. So we see this data set. We have four columns here that specify the length and width of the sepal and petals of these iris flowers. And the last one, species, is just a categorical variable. Categorical column where it tells you which category, which type of iris flower it is. So there's Setosa, there's like Virginica, and in the middle, there's just too many rows. So it only shows like the first 5 and then the last 5 rows. But in the middle, there is also versicolor. And down here, we see the dimensions of our data frame, which is 150 rows by 6 columns. Okay. Some ways to check or to inspect your data frame is using the head or tail functions. So you have your data frame dot head, and you can specify how many rows you want to see. So here I want to see 10. So it will give me the first 10 rows of the data frame. We can see it's all Setosa flowers. And then the tail, the same, you specify how many rows you want to see from the end, and it gives you the last 6 rows. If you want to see more technical info on your data frame, you can do irisdata.info, and it will tell you what it is. So it is indeed a data frame, and then it will tell you the range index, which is pretty much how many rows you have. And then it specifies for each column how many data points are not null in each column and the data type of each column. So we see the ID is actually just an int, but all the lengths and widths are floats. And then the species, because it's categorical, Python recognizes it as an object. And then it just tells you how much memory this data frame kind of takes up. So that might be useful depending on what you want to do. And lastly here, we can also look at the shape of our data frame. And it's pretty simple. It's just 150 rows by 6 columns, as we saw up here as well. Now, once we kind of inspect our data frame and see, yes, we have imported it properly, it looks okay, we might want to select subsets from it. We might not want to use or look at all columns or all rows. So here the syntax is again using square brackets, almost like indexing for NumPy arrays. So square brackets, and then you can write in the name of the column you want to see. So here I just want to see the species column only. It gives me the species column. Pretty straightforward. Also inspect multiple columns, and it'll return it in a data frame. So now the more interesting part is filtering data frames. Sometimes we want to look at rows or columns with a condition. And the easiest way is also just this square bracket notation. And inside the square brackets, we put the condition. So here I wanted to see all the data for only the Iris setosa species. So I have, this pretty much means take all the rows from the Iris data frame where Iris data species column equals Iris setosa. And if you can see here, everything it returns is Iris setosa, Iris setosa, setosa. Oh yeah, in this data set, there are 3 species and each species has 50 records. So here, yeah, we have 50. Okay, another condition, another example is if I want to look at all the flowers that have sepal length greater than 6 centimeters. So here we see that, oh, this is in order, by the way. So we see it starts at 51 and all the way to 149, but sometimes skipping different rows, and we don't have anything before this one. So that means actually setosa doesn't have any, as you can see, like setosa has ID like 51 to 50. And here, when we filter like this, we actually gain an insight seeing that, oh, setosa flowers, none of them have sepal length greater than 6. This is just something interesting. And sometimes there will be missing data, even though this data set is actually very well formed and there are no missing data, but there are no nulls in the data. But you might want to remove or not look at missing data. So you can use this function called NotNA, and this just gives you everything, every row that doesn't have species as missing data. But here we still have 150 rows times 6 columns because no data is missing, like I said. Okay, I will talk about the LLC and ILOC operators. This is when you want to select or filter on both the rows and the columns. So before, we just always, after a condition, we always get back like all the columns and we just filter out rows that does not meet the condition. But here, we might want to look at the type of species that have sepal length greater than 6 centimeters. This will only return us the species column. So this is kind of just like combining selecting columns with filtering conditions. And then with the LLC, as you still specify like the names of the columns, but for ILOC, also ILOC, you can just use indices. And this is similar to slicing. Here I specified 50 to 100. So this is the rows. I want 50 to 100 rows. And these are the columns. So I want columns 1 to 5. You can see we have rows 50 to 100, not inclusive of 100, and 1 to 5. So you see that ID is gone and then the species is gone. Maybe I just want to look at all the lengths and widths. So this is slicing. It'll give me a subset. It'll give me like a chunk of the data frame instead of all of it. Okay. Another useful thing to do is deriving new columns for the data frame. And this is also pretty straightforward. The syntax here is your data frame, and you put in square brackets the column you want to name as your new column. So here I set sepal length inch, and then I can perform a calculation on an existing column to derive data for my new column. So here I use the sepal length in centimeters. I divide by 2.54, which will give me the sepal length in inch. And let's just see what it looks like now. Our data frame, here we see there's the new column, and these values are in inches instead of centimeters. Yeah, so this is like one use case where you want to convert units. It's very helpful to just derive a new column. You can also use, you can derive a new column from multiple existing columns. So here I want to look at the ratio between petal length and petal width. I use the same syntax. Let's look at what it gives us. So we have another new column. I call it petal ratio, and the data is there based on the two existing columns. And speaking of columns, we might also want to rename existing columns. So maybe I don't like how long these names are and I want to shorten them. So this is done using the rename function. And I know I'm going fast and like this is some new syntax here, but just quickly, I want to rename column names and then equals curly brackets. And in the curly brackets, I do a list of old name colon new name. So that is the syntax. So here, old name, and I want to change it to this shorter name. And then for multiple columns, I just use commas to separate it. And we can take a look at what this renamed data frame looks like. Here we have, I just renamed 2 columns just to show, but it will be renamed like that. So it's very handy function. Okay, moving on. Oh yeah, anyone have any questions? Just let me know. Just see, it's too dark. Okay. All right. So moving on to summary statistics. So like with the NumPy, of course, in data analysis and like statistics, we need to look at things like mean and standard deviation and stuff like that. So there's a very comprehensive built-in function called describe. So if you just do your data frame dot describe, it gives you a good statistical summary of all the columns in your data frame. So including count, mean, standard deviation, minimum, the quantiles, and then the maximum of the column. So let's just see. Let's look at, I don't know, petal length. And we can see the count is just how many records there are in the column. That is not null. And then the mean of the column, when we see the petal length, averages around 3.76. And then standard deviation, minimum, the shortest petal length in all these flowers recorded is 1 centimeter. And then like the maximum is 6.9 centimeters. And in the middle is just the different quantiles. Okay, and sometimes we might not want all these summary statistics on all the columns. Like it doesn't make sense to perform the statistics on the ID column, right? Or yeah, it doesn't make sense. And of course you can't perform it on the species column since it's not numerical, so it just automatically doesn't include it. Oh, okay. So yeah, you can perform these for specified columns. You just, and for like specified aggregate functions. And then you can also combine filtering with these aggregate functions. So here I found all the flower IDs that have petal width as the minimum petal width. So this gives me all the IDs. And there are some other things where you can do group by. I know I'm running out of time here, but I'll just quickly go through these. So this one, you can specify which aggregate functions you want performed on which columns. And then you can also perform aggregate functions in groups. So here I want to do the mean of each species. So I use the group by function. And it gives me back a data frame with the average sepal length in centimeters of each species. And I just have some more examples with group by that I will not go over right now. And lastly, we can create plots based on these data frames. So just very simple. If you just want to take a look visually of how your data is looking, you can just do your data frame.plot. And it gives you just a very basic plot. But, oh yeah, actually, I'm gonna go back up. So here, I want to show you the plots without the new derived columns. So I will just rerun the code and okay. So yeah, it just gives you a really basic plot, but obviously we don't really want the ID to be plotted in here. So here I just have code that removes, that slices out the ID, and I do the plot again, and it shows us, so on the x-axis, it is all the different, like the different flowers, IDs, and then we just have the lengths, the different lengths. And we kind of see, you can see they're grouped. Like the first group is Setosa, and then this is kind of like a second group, which is the versicolor, and then the third group, which is the Virginica. Yeah, that's the name. Kind of tell from visualization. So that's where visualization is really helpful. And you can also just plot one column. You can also do scatter plots with different columns. So here I just did a comparison of length versus width of the sepal. This is a scatter plot. Oh, and alpha equals 0.5. It just specifies for each dot how transparent it is. So if there are like multiple dots on one place, I can actually like see them, that they're darker. And there are other types of plots you can do. So for example, box plot might be useful. Other types include like density plots, histograms, pie charts, bar graphs, line graphs. So there are a lot of things you can do with data visualization with Pandas data frames. And as an extension, you can also use a library called matplotlib, and that will give you more fancier plotting tools. Okay, and just wrapping up here. And NumPy versus Pandas, they're similar, but they have their use cases. So NumPy works with numerical data, Pandas works more with tabular data, and then NumPy has a array structure, but Pandas has the series and data frame structure. NumPy provides multi-dimensional arrays, and Pandas just kind of provides the two-dimensional data frames. And then for NumPy, it has better performance for 50,000 rows or less. So if you have smaller data, you might want to choose to use NumPy arrays. And then Pandas has better performance for 500,000 rows or more. So definitely if you have a large data set, you will want to use Pandas. And lastly, between the two, NumPy consumes less memory. As I said earlier, it's very memory efficient, and Pandas consumes a bit more memory. And here, for the resources I used or are useful, I talked about the NumPy documentation and Pandas documentation. So these are just the official sites for these two packages, and you can definitely just like Google NumPy or Pandas and you can go to the official site, and there's user guides on there, there's beginner guides, and sometimes even tutorials. So if you need to look, it's a very good place to start. Also, if you're more into like a course type of feeling, I would recommend LinkedIn Learning or other like online courses. There are a lot, and of course you can just look on YouTube as well. And if all else fails, you can just search on the web. There are many good websites and content for tutorials on these two packages. And that is it. I don't know if we have time for Q&A, but I hope you enjoyed this workshop and you learned something new. And if you have questions, I will still be here. You can ask in the chat. You're welcome, and thank you for coming. And yeah, just feel free to ask any questions. If you want to learn more, make sure to check out the resources I suggested, because just these 1 to 2 hours I cannot cover enough. There are so many more functions that NumPy and Pandas are useful for. Yes, and if there's something you missed today, feel free to check out the recorded workshop on YouTube afterwards.